Okay. Hope you enjoyed that little short. Okay, let's move on to reflection. Okay, can you quiet down in the back, please? Thank you. Okay, so like always, if you have any updated animatic or any updated materials that you would like to be critiqued, please submit them to the grade scope assignment if you haven't already. Let me check if anyone actually submitted anything. And I don't think anyone from Friday 2nd has submitted anything for critique. Unless you're planning to do it right now, raise your hands if you are, otherwise I'm just going to skip this. Okay, cool. Then let's move on. Okay, so today we're going to be talking about rendering and compositing. So I'll be teaching the first half of today's lecture. Also sorry, I'm feeling a bit under the weather, so sorry if my voice isn't projecting as far. But let's get started. So first things first, let's just look at how far we've come along. This is from the website here, and just like look at all the things that we have learned all the way up until now, right? We all learned how to model, how to shade, lighting, rigging, animating. It's, you know, you've come a really, really long way. So please just give yourself a pat on the back. Be proud of all the work that you have done so far this semester. But now we're moving on to the final thing, which is post-production. And the first thing we're going to do is cover an outline for today's first half of the lecture. So first we're going to be covering some fundamentals of like what rendering is. Then we're going to be covering render layers, some settings, and some ways to optimize. And then we just have a brief note on like real-time rendering for games. And then, this should be, sorry. Our Solda 330 tractor render farm and how you can use the render farm here in these computers as well. Okay, so first things first, fundamentals. What is rendering? Like, let's talk about the definition here. So rendering is basically the process of converting 3D images to 2D images. Or in other words, we're trying to simulate light, right? We have all of these scenes and these objects and these meshes and data, but how do we actually turn this into a 2D image? Rendering is the process of simulating light and simulating photons essentially to be able to create this 2D image. And we covered this a bit in the previous lecture, but just to reiterate, in real life, all the photons sort of like emit from light sources and they bounce around the entire world before they finally hit our eye. And once they hit our retina, our brain registers that as color. To simulate this in the digital world, what we do is we do this in reverse. So we shoot out photons from our eyes, or in this case rays, and they bounce around the world, and as they bounce around, they accumulate information about the properties of the objects that they interact with. And then, if they hit a light, that means that that ray must have originated from a light, because we do it in reverse, which means that that particular pixel is lit. So here's basically a nice graphic where this square right here is a pixel on your screen, and your camera is shooting these rays out into your world to be able to collect information about what it sees. Any questions? Cool. So here is a visual example of like everything we're doing. Basically, we have all of these objects, we have these models, we have these textures, we have these lights, we have these cameras, and they all exist as data and this information that is living inside our computer. But we want to be able to use this process called rendering to be able to consolidate all of these objects, all these independent objects, into a 2D image for our final render. So what actually is the process of doing that? Like how does that work under the hood? Essentially, use something called a rendering engine. A rendering engine is basically the software that is used to do the rendering process. And the key thing to note here is that this is different than your modeling software. For example, in this class we use Arnold, which is the rendering engine that is shipped with Maya. And it's it's built in, it's really nicely well integrated, but that's not the only render engine out there. There are lots of different render engines, each with their own unique quirks that allow you to achieve different effects because they simulate light slightly differently. So for example, you have Renderman, you have Redshift, you have Karma. So this is Pixar's one. This one is from Maxon, so the people who make ZBrush. This is from the people who make Houdini. There's Moonray, which is the one that DreamWorks uses. And you have Cycles, which is the one that Blender uses. So the important thing to note here is that because they are separate softwares, a lot of the times you can actually use the same rendering engine in a different software for its own specialized purpose. For example, if you've like messed with the plugin, like sheets on Maya, you might have seen what M2A, and you check that on and it enables Arnold for Maya, right? Because this stands for Maya to Arnold. While if I were to use Arnold in a different software like Houdini, then it would be H2A, because that'd be Houdini to Arnold. So understanding how you can use like the same render engine for different softwares is how a lot of different studios are able to have like pipelines across multiple different softwares just by porting over their render engine as a separate software and integrating those within whatever software you choose to use. Yeah, I think of these ones, Redmond is free. This one has like a free non-commercial license, which is really nice. Other than that, Moonray is also free, but this is like impossible to install. I tried, it's really hard. And then you have Cycles, which comes shipped with Blender, which is nice, but it's also really difficult to integrate with other softwares. It's kind of baked into Blender, but it is there. Everything else costs money. Okay, let's move on to IPR rendering. So IPR rendering stands for Interactive Photorealistic Render. Or in other words, when you open up your viewport, when you click the render button in your viewport, this is what happens. That process is called IPR rendering. And it's basically preview rendering because it allows you to see your scene instantly, and any changes that you make to your scene are instantly reflected in the render. There's a bit of a trade-off where the quality isn't as good as if you were to run like the actual like rendering pipeline process. However, it's really, really good to be able to sort of preview your scenes, and that's what you've been doing when you're clicking the render button. Some like cool features that it has is that you can like drag like a crop window on your screen, so you can only render like that specific part of your window. You can change the resolution of it. You can view different AOVs or debug statistics. And this is basically IPR rendering. But if we want to actually render something out like for a final short, what we're going to be doing is something called sequence rendering or batch rendering. So sequence rendering is the standard rendering procedure. It's what you're probably going to do on your own laptop and your own machines in the future. And it's really, really easy to set up. So essentially what sequence rendering is that, like the name implies, you have a bunch of frames in a sequence, and then it renders frame 1, and then frame 2, and then frame 3, and then frame 4, and it goes on until it finishes rendering all your frames. So because it is 1 by 1, it is pretty slow because you have to wait for one frame to render before you start the new one. And also because it uses up all your computer's resources, it kind of like locks your computer into jail. Like you can't use your computer while it's rendering. If you click that render button, your computer is cooked for like 10 hours or more, depending on how intensive your scene is. So just be wary. Usually if you're sequence rendering, you just run it on overnight. You leave your computer on overnight. In the morning, pray that nothing errored. If something broke and your render like crashed like 2 hours in while you're asleep, then you're just gonna rerun the render. So it's what you're gonna be doing to like render on your own. It's kind of finicky, it's kind of frustrating, but that's just how it is. The alternative here is called batch rendering. So what batch rendering is you're rendering over a network, which means it's not necessarily as accessible towards like normal people.
We require your
but
assistance
if you have
when
access to
examining the
multiple
rig.
computers, like a farm of computers, what you can do is that you can distribute all your frames out to that network, such that each computer in that network renders a certain portion of frames all at once at the same time. So for example, if you have like 30 computers, you can render 30 frames at once, and it will just cycle between all those, and you can drastically cut your like render times down a lot. The downside to this is that it's really difficult to set up. Like one, you need like 30 computers or like a bunch of different computers. Two, you're required to like code, and you have to like actually understand how to network between the computers and integrate it and all this stuff. And this is usually the work of a technical director or a pipeline director in a studio. And also certain like renderers have certain licenses that have certain requirements saying like, hey look, if you're going to be using batch rendering, you need to pay more money, right? Which is what like Arnold is, but because we have the educational license and like the school has like a deal with Autodesk, we actually get access to batch rendering. And this is what we're going to be using if you're going to be using the render farm in this computer lab. So this computer lab, all of these computers that you see here are actually a part of a farm, and you could run like frames across all these computers. It's kind of cool. Like you run a frame and then all these computers all at once, you start like and they turn on. It's kind of cool. But yeah, so that's batch rendering. It's not really possible to do on your own, but if you have access to resources, that's what you're going to be doing. Questions? Okay. Okay, let's talk about samples. Again, we talked about this a bit in the light samples area, but let's get more in depth here when we're talking about rendering in general. So basically, as a theory of why sampling is necessary, in real life, there's an infinite number of photons, and there's also an infinite number of ways that they can bounce, right? So when we're doing computing, we need to be able to sample that, or we need to be able to approximate that. And sorry, can you quiet down in the back? Judy, Travis, can you please quiet down? Yeah, so what we're going to need to do is we need to approximate this, right? So the process of approximating this infinity, this true image, is called sampling. So over here is a nice little graphic where if we're shooting rays out from the eyeball and it hits the surface, technically this light ray can bounce in any direction it wants, and only one of these directions is actually going to end up hitting a light, right? So we need to be able to approximate this randomness, right? So the number of checks or directions that we test to see if hey look, is light coming from this direction? Hey look, is light coming from this direction? Is light coming from this direction? The number of times that we check that is called a sample. And when we have higher samples, that means we're getting closer to this infinity number, which means it is we get less noise, it looks better. However, it drastically increases our render times in such a way that if you look at this is actually exponential. So from 1 to 2 samples compared to 2 to 3 to 3 to 4, it exponentially increases the number of time it takes to render something. So be wary for samples. Sometimes you can't just oh, I'll have a million samples and everything, because then you're going to be locked in the jail, right? So yeah, this is what sampling is. Does anyone have any questions about sampling? Yeah, so here's an example. This is just the GIF from last time, blowing up. So here, what they're doing is that they're clicking a specific pixel, and all these rays that shoot out are the directions that we're checking for lights, and each ray is a sample. So we're sampling in that direction, and you can kind of visually see what directions it's checking here. Here's a visual example of what noise is. So when you're unable to approximate when you don't have enough samples, you get something called noise. And over here, if we have one sample per pixel, you get this really, really noisy effect where it looks like static and grain applied to the top of the image. Well, if we increase the number of samples, the image clears up, it becomes a lot smoother, and we get this sort of less of this staticky vibe, which is the noise, essentially. So ultimately, one of the main goals of rendering and what we're going to be doing is how do we optimize our settings, and how do we render in such a way that we can get rid of the noise as much as possible while also trying to reduce the amount of time it takes to render something. Because sure, we can just turn up the samples, but if we turn up the samples, it's going to take forever. And if it takes forever, then we're never actually going to get a final render. So trying to find that nice balance is the ultimate goal, essentially. Here's just another visual example. Say this image right here, this is the true representation of the scene. And because we need to be able to approximate that using digitization, we're basically approximating the true image. And if we have a low number of samples, then we're not going to be able to approximate it effectively. But if we have a high number of samples, we're approximating it a lot more effectively. Okay, so sampling is directly related to the ray that it shoots out. And we talked about how we're simulating these photons as rays. There are actually a bunch of different types of rays, and here are some of the types of rays that you can manipulate in your rendering software. So first is the gamma ray. So these are rays that are emitted from the camera. So the photons directly that go into the camera, this is what it represents. It is the gamma ray. And the important thing to note is that it doubles every other ray type, and we'll get into why in a bit later. Next is the diffuse ray. So a diffuse, as you remember, is a diffuse surface, so it's a shader attribute. So anything that has a base color, right? That color has a specified diffuse ray that is attached to it to be able to gather information about that object's color. You have specular rays, which are rays related to the object's reflection or specular property. You have subsurface scattering. You have transmission, which is for like transparent objects. You have volume rays, so if you're working with like volumetrics, clouds, things like that. And you also have light rays, which we covered last week, which are related to lights and shadows and how bright a surface is. So here's a visual example of the different types of rays. So over here, you have this eyeball, and it's kind of shooting a camera ray. So this yellow ray right here, this is a camera ray through a pixel, and this is your pixel. And then once it hits an object, these green arrows right here are diffuse rays. And if you kind of like imagine like intuitively like what this means, when you have like your screen here, a pixel is like a specified width, right? Like you have your sensor of projection, and like all the light focuses on to your eye, but when you have a screen in front of you, the pixel itself is like, it has like a width, right? You have like a width of a pixel. So you can shoot your camera ray like through the middle of the pixel, through like the upper right hand corner of a pixel, and if it like shoots in a slightly off area, it might like hit a different object, right? So the number of camera rays is directly related to the number of rays in slightly different directions that you're shooting through a specific pixel. That camera ray, once it hits an object, needs to be able to collect information about the object's diffuse color. So in this sense, right, the diffuse is spread randomly throughout this hemisphere of this object. Because if you imagine light can hit this object from here and then bounce over here, or it can hit the object from here and then bounce over here, or it can hit from here and bounce up here. And since we're doing it in reverse, we need to be able to send out diffuse rays in random directions to be able to see, hey look, for this diffuse color, this diffuse property of this object, let me check to see if light is coming in from this direction. And this is specifically for diffuse, but you also have individual checks as well for their specular property, right? Because in specular properties, it's a reflection. So you check in the reflective direction, and you have maybe, if it's not like a perfect mirror, then you have like slightly different angles that reflection can come from. So over here, this is diffuse. You have glossy and specular, which is like just reflective properties. You have transmission, so the camera ray or any individual ray like hits an object, and to be able to collect information about that object's transmissive property or its transparency, it shoots rays through that object to be able to collect its transparency information or what's on the other side of that object. Yeah, and these are volumes, which is like at every step it encounters the volume, it like shoots up random rays and stuff. You don't really have to worry about volumes, but these are the different types of rays. Does anyone have any questions about like these graphics? Hopefully it helps sort of like understand like what the different types of rays are. Okay. Next, let's talk about ray depth. So just like, you know, the whole thing about like approximation, in real life, light can bounce around infinitely, right? In digital world, we need to kind of like truncate that. We need to be able to like approximate like, hey, look, we can't test this ray hitting an object and hitting another object and then another object and another object like infinitely, right? We can't do that infinitely. So we need to define a depth to be able to just give up, essentially. Like, hey, look, we tested that this ray hit like 2 objects. Let's just cut it right there. Like, let's not test anymore. It's a waste of resources to be able to constantly like try to guess like, okay, is this ray eventually after like 50 bounces is going to hit a light, right? So the ray depth is basically saying, when do we give up trying to check the ray like moving, and once it like gives up, well, like once it like bounces around to the specified ray depth, then it will just return a black pixel, where it's like, hey look, it's just black. So over here, you can see this phenomenon like really clearly, especially with transmissive surfaces. So for transmission with like transparent objects, let's say the ray depth is 2, and I have 10 glass panes stacked on top of each other. Well, if it's the ray depth is 2 and like the transmissive ray just hits 1 glass pane and goes through it, and that's just it, that's 1, right? That's 1 bounce, right? It hits an object, it bounces once, there's no issue, I collected the correct amount of information. But let's say I'm like going through 3 different like glass panes, right? So I hit the first glass pane, that's information about 1 glass pane, and then I hit the second glass pane, right? That's 2 glass panes. But because our ray depth is 3, it will never go fully through the glass panes, and it'll just say, hey, look, let's give up because we never encounter the light, because it has to go through all 3 of the glass panes to be able to hit the light in the back. Then we're just going to return black, right? So that's what you see over here, where you see it like look properly transparent in if it like goes through 1 glass pane, but if it like is stacked, then it looks just black. It looks wrong, right? Where if you increase the amount of ray depth, then it's able to puncture, or it's able to bounce through more of these like glass panes and actually hit the light and then collect information about the light before it gives up. Does this make sense? Does anyone have any questions? Is anyone too confused that they don't know what question to ask? Okay, cool. So the ray depth is actually specified for every single ray type that we mentioned before. So you have your diffuse ray depth, your specular ray depth, transmissive ray depth, volume ray depth as well. So this is just like, when does it stop checking to give information about like the type of ray. This is a brief note on caustics as well, because we're talking about transmissive surfaces. So caustics are essentially like refraction. So light can like hit an object that is refractive and focus into a specific location. And these tend to be really, really noisy. And even if you have like 1,000,000 samples, they'll probably still be really noisy, and it's really difficult to actually clean up. There are very specific ways on how to render these types of things, these caustics. But if you're curious, you can talk to me after class. But TLDR, if you have any of these in your short, I would consider just like trying not to do that, because it just looks bad otherwise. By default, Arnold actually turns off caustics, where it's saying like, hey, this material will not have caustics. So you have to like click a button to be able to turn these on. But yeah, this is caustics. These take really long to render. And as a bit of like a thought experiment, like on your own, try to think about like, given what you know about sampling, and given what you know about this reverse light approximation, why do these take forever to render? And the key important thing to note is that like, because it is refractive, that means that light can only hit this one area from one very specific direction. And if we're sampling from a bunch of different random directions, the chances are we're going to collect the correct information about this light is very, very low. So yeah. Okay, quiz. What type of ray is causing this issue, and how would I fix it? So first, identify the issue, then identify the type of ray that is causing the issue, and then identify the solution on how to fix it. So please discuss amongst yourselves for a bit. Okay, does anyone have any ideas? Yes?
Is it that there's not enough light?
Can you be more descriptive?
Oh my god. I don't even know. I was looking at guys. Well, see, that's like dark, like black basically.
Mm-hmm.
I feel like the way that the camera is angled, or not the camera, the light is angled, makes it to where that's like the dark spot. That's why I think like it's the light, but I'm not too sure what that answer
Okay.
is.
This is a wild guess, and I might be fatally wrong, but is it because of the specular, or no?
Close. Yeah, it is because of the specular, but what about the specular is wrong? Any ideas? Okay, so when you're like thinking about this sort of problem, like first identify like what is the problem. Over here, you can see you have 2 sort of like really reflective balls, and over here, it's a bit small, but there's just like a black sphere. It's like pure black over here, right? It's like they should be reflecting into each other, but after a while, it just stops and it's just black. right? Does that sort of remind you of a certain ray depth issue, right? So over here, essentially, like what's happening is, one, it's a specular value. It's a specular value that is like causing the problem, and the reason is because these are specular balls, right? The balls themselves are reflective. It is a specular value, so it has to be a specular ray, right? So it's not a camera ray, because if it was a camera ray, then it would be something with the image and not with the specific ball, right? If it's not diffused, because these aren't diffused surfaces, it's not subsurface, because these are not subsurface surfaces, and so on and so forth, right? And it's ray depth because if you think about like reflective balls, if you've ever been into like an infinity room, or like you've had two mirrors facing each other, right? Light hits this object, and then it hits this object, and then it bounces and hits this object, and then so on and so forth, right? Almost like infinitely, right? So if we like give up after two bounces, then we're gonna say it's hit this object, it's this object, and then let's stop, let's give up, right? And then you're gonna get this like really black sphere over there because you're not bouncing enough through these surfaces to be able to collect enough information about them, right? So this is a specular problem, it is a specular ray, and it is the ray depth that is the issue. Make sense? Is there any questions? Any confusions? Yeah, so understanding this is really, really important because when you're evaluating your renders, you want to be able to like, hey look, why doesn't this look the way I want it to look? Why does it look wrong? And sort of being able to have the technical capability to deduce what is actually causing the issue is very, very important. Okay, here's some settings. So basically, like, how do you manipulate all these like rays and these numbers in Maya? It's a very simple button. Like, there's a render settings panel, and you just like change the values. So over here, you can see like, oh, how many like camera, diffuse, specular, transmission, subsurface, and volume samples do I want, right? And you basically change the sliders here. And over here, it'll total them all up. So not counting for light samples, it'll total them all up. So by default, these are the default settings. There are a maximum of 180 total samples. And notice here how if we have like 3 camera A samples, the maximum number of samples that we have across everything is 180. But with 4 camera A samples, that was 320 total samples. Like what? I increased this value up by 1, and like the number of samples like went from 180 to 320. Like what happened, right? So the reason this is happening is because the camera AA value is actually a squared value. So when you're saying like there's a camera A value of 4, this is actually 16 or 4 squared camera samples. So a camera A value of 3 would be 9 camera samples for 3 squared. And another thing to note here is that every other like sample type spawns from a camera sample. So when a camera sample is the first ray that shoots into the world, once that ray hits an object, then it will spawn a bunch of these other rays to collect information about that object. However, if I have like 2 camera rays, that means I'll shoot out 2 rays from the camera, and each of them will spawn all of these, right? If I have 3, then it'll spawn 3 of these, right? So since like they're directly related to the camera rays, by increasing the number of camera rays, you're also multiplying the number of like diffuse, specular, all these other rays by the number of camera rays, right? So those 2 properties are why like if I increase the number of camera AA samples from 3 to 4, it goes from like 180 to 320, right? So it's just a thing to note where like, hey look, it looks noisy, I want to be able to get rid of the noise. The easiest thing you could do is to just increase the number of camera samples, because the number of camera samples is like, it applies to everything, right? It's just the amount of light that's coming into the camera, more camera samples, less noise, right? However, it also really drastically increases the number of other rays that comes out, right? So let's say your noise is actually related specifically to the diffuse property of the object. Like the diffuse property is causing the noise because you're not sampling the diffuse property enough, right? Then if I'm increasing the camera samples, then yes, I'm going to end up sampling more diffuse because like each camera ray will like create more diffuse rays. However, each camera ray is also creating more specular rays and transmission rays and all these other rays, right? Where let's say your object is like slightly like specular, then you're saying like, hey look, the specular isn't contributing to the noise, the specular actually looks good, but now I'm spending more computational resources trying to calculate the specular value because instead of increasing the diffuse rays, I increase the number of cameras handled, right? So understanding like, okay, this is the noise, what type of noise is this? Like, where is this noise coming from, what property? And how do I manipulate these sliders in such a way that I only target that property without using like a blanket, like, hey, let's just increase camera samples, it fixes everything. Because then you end up spending a bunch of computation and a bunch of energy trying to calculate something that doesn't matter. Does that make sense? Yeah, okay, cool. But honestly, otherwise, like, if you're like too lazy, you could just increase the number of camera samples. Like, it is like the goal fix. Like, it works, right? It works for a reason. But specifically, like, there is like very minor situations in which it doesn't work. For example, we talked about light samples last week, and the reason is that the number of camera samples actually won't help you in shadows, because for shadows and noise specifically related to shadows, that is due to not being able to sample the light enough and not the number of cameras. So like, camera samples will work for everything except shadow noise, because you need to increase the number of light samples related to the specific light that is casting the shadow that is causing that noise. Okay, questions? Okay, let's move on to render layers. Sorry, I know this lecture is just like a bunch of information, and it's like seemingly like just kind of like all over the place and like really like not connected. That's because like a lot of rendering is just like content and just like a lot of math and like all this stuff. So yeah, just please bear with me. But render layers. So if you've ever used a 2D art program, you might be familiar with layers, where you can sort of draw one thing on one layer, and then you draw another layer on top, and then it'll like stack on top of each other, right? We can do the same thing in rendering, where when we render something out, we don't have to render it into one 2D image. We can render this out into multiple layers and have multiple images come out of our render. So this process is called using render layers. So over here, we can have the foreground, the midground, and the background all out in separate layers, essentially, and then we could be able to manipulate each layer individually in post. So basically, we can separate like different parts of our short into separate layers. So why do we use render layers, right? One of the primary benefits of using render layers is post-processing, right? So let's say like I had everything in one layer, and I'm like, okay, well, the background is a bit too dark, right? Like I rendered this out, but like I'm like, the background just doesn't look right. But the character looks fine, the foreground looks fine, it's just the background that doesn't look good. Well, I can't just increase the brightness of the entire image, because if I do that, then everything increases, right? Because it's one image, right? I can manipulate the one single image like file. However, if I had multiple render layers, if the background was on a separate layer, then I can manipulate that specific layer on its own, right? So when you think about post-processing, just having more image files, more data to work with is really useful to be able to sort of like edit things in post. Another thing is like VFX, right? So when you're talking about like working in like a major studio, a lot of studios use a lot of different softwares, and each software renders out an image in that software. For example, if I'm making an explosion in a software like Houdini, I can't like take that explosion, move it into Maya, and then render it out in Maya and get one image. I need to be able to composite it together because I'm using their own software for their own very specialized needs, right? So now I have like this explosion, and I also have my render, and I want to be able to put this explosion in my render such that it feels like natural, right? But if it's just one image without using render layers, then I can only either put the explosion in front of everything, or completely behind the entire image and you can't even see it, right? So how do I sandwich this explosion between the foreground and the background? Well, then you would have to use render layers, right? You would have to separate the background and the foreground so that you can put this explosion in between, inside, or like sandwich it, right? So when we're talking about VFX, and when you're talking about like trying to insert other images into your scene in post, using render layers is very, very important. Additionally, if there's a tiny issue that you found out like later, it can save you the process of re-rendering, because you could just edit that layer in post rather than having to run the entire rendering process all over again. Another thing is like, okay, well, if I have render layers are so useful, why don't I just create like 1,000,000 render layers, right? I just like render layer everything. Every single object is on its own layer. You could do that, but then like these are their own individual files, which means it eats up your storage, right? Like files, like file sizing is like a real issue where it's like, hey, look, you can have a lot of render layers, but is it useful? Does it provide you the control that you need? And is it worth having all of these files all taking up file space? So here's an example of the application of render layers in Disney's Frozen. So over here, what they did is that they rendered Elsa and the background in separate layers, such that in post they were able to take this like background layer, they were able to blur it a bit, and then they were able to desaturate it a bit, and then they would take Elsa and then up their vibrancy to make her a lot more saturated to make her pop out in the scene, right? And this isn't something you can just do in render where you can't just like, oh, I want to like artificially blur it, I want to artificially make the background more desaturated, right? And then make Elsa brighter like for this specific scene. It's not really possible and it's like kind of difficult to do. So by having render layers, you're able to actually like achieve this process. So this is what they did in Frozen. And the important thing to note here about render layers is that it's not the same thing as just hiding the object, right? Like you're like, okay, well, can't I just like render Elsa without the background? And I just like hide Elsa and then I render her with background, now I have two images, right? It's not the same thing because in a render layer, like Elsa has all of the lighting information from the background, and the background has all of the lighting information from Elsa, like her shadows in the render layer, even though she's not there, right? So it's physically like cutting out that object in the rendering process, right? It's like, hey, look, this is the scene as if it would look, just without that object being drawn to the screen, right? So that's why render layers is like, it's not the same thing as just like hiding an object. It's specifically isolating certain parts of the final render into multiple different frames. Yes?
With render layers, how do you exactly like keep the shadow?
Yeah, so the shadow is just captured by default. Like if I like select Elsa and put her in one layer, I select everything else and put that in a different layer, and I create this, it'll create two files. And one file will be just Elsa, and the other file will be just the background, including Elsa's shadow, because Elsa's shadow is not a property of Elsa, right? It's a property of her effect on the background. Like the shadow is a part of the background. However, if I don't want that shadow, you can also turn it off. Like you can just, there are certain like shaders you can do, there's certain settings you can do to basically like, hey look, I want to cut it out. You can also matte out, like let's say I want to cut out of Elsa where it's just like her silhouette, like cut out, you can also do that. So you can do a lot of things with render layers. But yeah, does that answer your question? Cool. Here's another example. If you've ever watched anime, you know how like sometimes the eyes are like on top of the hair, even though the eyes are like behind the hair, and you're like, what the hell, how do I do that, right? It's not possible to do in 3D. Well, if you have the eyes and the eyelid and the hair and everything else in separate layers, then in post you could just take the eye and put it in front and then use like a transparency thing to like be able to accomplish this effect, right? You can't really do this in render. You would have to use this in post, and you would have to use render layers. Questions? Cool. Yeah, so here are just some applications of like why render layers are important and useful. What do they look like in Maya? Essentially, this is your scene. It's created like a collection of layers. Each layer is like has a collection of meshes, essentially, right? So your Maya file, there's a bunch of layers. You can find your layers. Inside the layer, you create a collection, and the collection has a bunch of meshes. And each collection has a bunch of properties associated with them. This is what they look like. It's kind of like there. I'm not going to go too in depth of this. There's like a whole thing, but if you're interested, this is how the render layer process works. Generally speaking, you probably won't, like for your shorts, be using too many render layers, or much at all. If it just looks good in render, you're fine. Or if you don't have much time to actually do post-processing. But this is what it looks like in Maya, essentially. You can refer to these slides, or just search up on your own afterwards. Questions? Okay, what time is it? Oh my god.
7:50.
Oh, okay. Let's talk about optimization. So we talked about this whole rendering process. I constantly reiterated that like rendering takes a really long time, and like all these samples, like okay, look, we're spending extra computational resources and everything, right? So how do we actually go about the process of making something render faster, right? For example, like let's say it takes me like a minute to render a frame. You're like, oh, that's not that bad, right? It's a minute to render a frame. Well, if you think about it short, it's like what, 1 to 2 minutes long, right? Which is 60 seconds per minute, which is 24 frames in a single second, right? Like 24 frames a second, right? That's like over 1,000 to 2,000 frames, right? And if you're like multiplying that by the amount of time it takes to render one frame, then like your entire short might take like a few days to render, right? So optimization is really, really important, especially if your render times are pretty long, right? So what's the first thing you do when you're optimizing? Well, lower samples, right? That's like, if samples are the thing that's causing the issue, you could just lower the samples. So it's not good to have a bunch of samples when you don't need them, right? There was this one short in the past that like had their camera A value up to 20, which is the max. So 20 camera A means 20 squared, so 20 times 20 camera samples. And they basically maxed out every single slider, and I was like, please don't do that. And then they ran it through a farm and then drained a bunch of money. But essentially, like, you don't need a bunch of samples if it's not necessary for your scene, right? So the core tenet is use the lowest amount of samples to be able to achieve a good image without having to actually like compromise on quality, right? And the same goes for ray depth. The default ray depth is 10, which is a lot, right? So like sometimes you don't need this much ray depth. Like I lower it from 10 to 3 and it still looks the same, right? It's basically imperceptible. So you don't need to spend all that processing power doing more ray depth, more bounces when you just cut off, right? Another thing is like, let's say like you have an object and it has like a very small amount of subsurface scattering that is really necessary, but it's not like actually like super visible, then lower the amount of subsurface scattering samples, right? Like you don't need it that much. If the primary color is from the diffuse and the subsurface isn't a prominent part, then it's just adding up to your render time when you don't need it to, right? So think about the properties of your scene. Think about sort of like how, like, okay, what is important to the scene, what is contributing directly to the quality, and then lower the amount of samples otherwise. I think the default Maya samples are kind of high, actually. So just lower those, and then you can bump up the camera A samples where it's like, okay, look, maybe I don't need this many diffuse samples. I can have more camera samples, but less diffuse samples, and that actually gives me a better render quality than if I were to just like do it, like not do that, essentially. Yeah, basically, if you have shadow noise, it's your light samples that's the issue, not your camera samples. But yeah, so by sort of adjusting your samples, that is the primary way to optimize. The second way to do sort of this optimization is denoising, where denoising is like you're just getting rid of the noise. You're like, what the hell? What? You just get rid of the noise? Why didn't you tell me that earlier? Right? So denoising is actually a separate process, a separate algorithm that is applied after you finish rendering. So over here, you can sort of render with some noise. You're like, hey, look, this noise is okay, because we know that when we apply our denoising, after we render our denoising algorithm, it'll basically just get rid of all that noise, right? So denoising is a separate process that is applied after you render, and it has to be really quick, or a lot quicker than the whole like rendering process, right? And why this is useful is because you can spend less time trying to get rid of all of these samples when you could just apply a denoising algorithm after it and get rid of the noise while keeping your render times low. The important thing to note about denoising is that denoising is actually like something that is available in a lot of different softwares. You could do it in Maya. You could also do it in like After Effects, or you can do it in like whatever program of your choice, right? But the important thing to note is that no matter what software you use, it's important to make sure that your denoising algorithm is temporally stable. Now, what does this mean? This basically means that like when you denoise, you need to make sure your denoising works for animation and not just for a still frame. There are certain denoising algorithms that only work for single images, and certain ones that are specialized for working across multiple frames or essentially for animation. Maya actually comes shipped with 3 types of denoisers. You have your NVIDIA optics denoiser, you have your Intel Oiden denoiser, and your Arnold denoiser noise. And only the Arnold denoiser noise is actually like animation ready, while the other ones do not work for animation. Where like if you try to use it for animation, you end up getting a lot of flickering. So here's an example of that flickering.
So firstly you have the optics denoiser, which, as I said, is more suited
You can
to
kind of see how
IPR
there's a
rendering
lot of like
and
flickering,
fine frame
especially in this
animation.
area.
It does a very good job, but you can see there's a lot of wobbly instability in the
Especially
animation there. Same goes for the Intel Oiden denoiser. Again, more suited to IPR than final frame animation, but again, we're getting a lot of instability in the animation. And then here we have the Arnold denoiser noise.
Right,
Quality is better, but there is still some instability between the frames.
Yeah, so basically make sure you're using a temporally stable denoiser, otherwise you end up getting lots of wobbly effects, which don't look good. Questions? Cool. Okay, so let's talk about imagers a bit. I'm not going to go into imagers too much in this class, but if you're curious, you can talk to me. Essentially, like Arnold comes shipped with a way to do post-processing in Arnold in Maya. So you apply these things like imagers, which are like post-processing effects. And it's nice if we're just running a single image for preview, but like we're not going to be using this because we're using our own special compositing softwares. But the important thing is, as of the latest Arnold version, a default denoiser imager is actually automatically attached to any single new scene that you have. So every single new scene has this Arnold denoiser imager applied to it. And this is really useful for IPR rendering because you want to be able to preview your render and just see what it looks like without noise before you actually if you're testing things, messing around shaders, moving objects around, you want to be able to render that really quickly. You want your IPR to be quick, but also without noise, right? So that's why this denoiser is attached to every single scene, because when you're doing IPR, it's very useful. However, when you are doing your final render, you need to disable this, you need to delete this, because this is not a temporally stable denoiser. This is specifically only for your IPR preview rendering, and if you don't have this, then this imager is going to be applied to your renders, and then it's going to be temporally unstable, right? So make sure you don't do that. Just turn it off before you finish rendering. Yeah. Okay. So checklist, essentially like a checklist of all this optimization and the stuff we talked about. How do I optimize, right? 1, reduce your samples and your ray depth, right? There are specific shaders you can use that are really complicated, but if you want to be like, hey, look, I want this shader to like say, hey, look, from this object, I want more samples, but from this object, I want less samples. You could do that through a shader. It tends to be a lot more complicated though. But TLDR, just reduce the number of samples, reduce your ray depth. And also use denoising algorithms, right? It's okay to render with a bit of noise if we're able to just denoise it afterwards. So make sure you do tests, render a few frames, test the denoising algorithm, test to see if the settings work before finally sending out your full render. Additionally, hide unnecessary objects from your scene. For example, if something is not casting shadows, not contributing to the color, not contributing in any way to the scene, like I have a building in the background that's like not contributing anything to the scene, hide it, right? You don't need it. It's just going to contribute to render times. Additionally, it's also like you should have different render settings per scene. So each scene that you have has its own unique needs. For example, if I have a scene with a lot of transmission, then I might want to focus on that transmissive sample count. Well, if I have a scene with a lot of diffuse and no transmission, then I want to focus on diffuse samples and less transmissive samples, right? So looking at your scene, look at what does this scene need, what shaders are in this scene, and optimizing to do that is really necessary. Additionally, reduce polygonal complexity. For example, if I have a cube and it's like 500 feet away and I can barely see it, it doesn't need 50,000 polygons, right? It doesn't need 50,000 faces, right? So if you have an object that's really far away and you're not able to like see it properly, then it doesn't need to be so detailed. While if it's like really close up to the camera, if it's a hero shot, then yes, it does need the detail, right? Additionally, you can GPU render. So GPU rendering is actually quite finicky. Most offline renders, or most like renders in like for film and animation, tend to be CPU focused. And the reason is because not all of the properties of a CPU render can be easily ported over to a GPU render. And GPU rendering tends to be a lot faster, but it just doesn't have enough features, or doesn't have as many features that a CPU rendering like has, right? So if your scene like very specifically works for GPU rendering, then you could just run it through GPU rendering, which is really nice. However, if your scene doesn't work for it, then you're going to have to stick to CPU rendering. For example, if you're toon shading, GPU rendering does not work for toon shading. As of the latest Arnold version, like it kind of does, but shadows don't work. I believe shadows don't work, which is kind of like, well, it's kind of important, right? So, yeah, just make sure like if you're seeing like works for GPU rendering, by all means go for it. Just make sure you test things to make sure it looks good. I think like of the render engines out there, I think like Pixar's Renderman and Maxon's Redshift are kind of the only ones that are like production ready for GPU rendering, or like XPU, which is like combining CPU and GPU. Like Renderman like recently just released its latest version. It's like, hey look, we're finally production ready for XPU, right? And they're using that in the new Toy Story 5, right? So Arnold is not one of those, unfortunately. Next is reducing the number of lights. You should not have more than like 4 to 5 lights in your scene, right? The number of lights exponentially is related to the amount of rays that you have, right? Every single ray that you have is multiplied by the number of light rays you have, multiplied by the number of light samples per light, right? So reducing the number of lights, you don't need 100 lights, you don't need 50 lights, right? Just use the minimum amount of lights to be able to light your scene, and don't use more than that. Otherwise, it's going to really, really increase your render times. Additionally, reduce shader complexity. There are certain parts, like certain shader attributes that make your render time really, really long. For example, specular roughness. So if you have a roughness attribute in your specular, that's really intensive. Subsurface scattering tends to be really, really intensive. Same with displacement maps. And this is a bit of a meme and a bit of a joke. It's like, oh, no, things don't look good in the render. I'll just fix it in post. You know, I'll fix it later. You know, that's someone else's problem to worry about. Yeah. If you've ever like been in a film set, you're like, oh, I'll just fix it in post. I'll fix it later, right? Same thing can kind of apply where it's like, hey, look, like it looks a bit bad. It looks a bit like noisy or whatever. I'll just fix it later, right? Which is also like kind of what denoising algorithms are, right? Where it's like, hey, look, there's a lot of noise. Let me just apply denoising algorithm after I rendered. Also, there's this right here, which is nice. So this is a link. Arnold actually has a workflow diagram where it's like, it's literally a flowchart saying, hey, look, do all of this stuff. Is there noise? Okay, yes. Then keep doing this, keep testing this, all the way until the end before you hit your final render. It's a nice flowchart, nice diagram for you to refer to if you want to sort of like a visual guide on like, okay, what specific, very specific steps should I do if I want to like denoise things properly. I will say a lot of these things are very technical and probably are out of scope of your short, but it is good reference. Additionally, Arnold also ships with a diagnostic statistic report. So when you render, you can it'll output a HTML file. So it'll basically create a website for you that has the diagnostics of your entire render, including how long it takes to render a frame, what specific materials, attributes, shaders, objects, meshes are contributing to that render, the amount of time it takes for every specific part of it. So there's like form, memory, geometry, your shading, your rays, your textures, like it's very, very useful for identifying like what specific problem it is, right? You can just enable this. You can look at this report after you finish rendering. You can identify like, hey, look, why is this one specific shader making it like take forever to render, right? Then you can sort of adjust it from there. All right, questions? Yeah, questions? Yeah, I know that was a lot to cover, but yeah. Okay. And moving on, we basically, like, if that was a lot and you kind of don't remember anything, it's like, oh my god, thinking is too hard, that's so real. We actually have a lab for you called the Rendering Arnold Lab. It basically goes through all of your render settings, and you can kind of just like, this entire lecture is like summarized really nicely in this lab right here. Yeah. TLDR, make sure you have your image size properly, render in HD 1080p, make sure you're not rendering in 4K, please don't do that, that's going to take forever. Make sure you're not rendering in 520p, right? That's just going to look bad, right? Make sure you start and end frame properly, right? Like if you have like 1,000 frames, render those 1,000 frames. Don't render like 10 frames and like oh, okay, I'm thinking I'm rendering 1,000 frames, but I actually only set to render 10 frames, and then I go to sleep and you wake up and only 10 frames are rendered, and you're like, what? Right? Your file extension type is EXR. We'll be talking about this more later in lecture. Filters, if you're using toon shading, make sure you have contour enabled, otherwise your toon outlines won't work. ALVs, we'll talk about this in a bit. Make sure you're denoising, and make sure you look at your sample count. Okay, so on to our next big topic, color spaces. So what are color spaces? So basically in real life, your eyes have 3 types of cones. Your L, M, and S cones that correspond to different light, spectroscopy sensitivities of like light, right? And like we can see a bunch of these colors and like all of these colors using our eye, but a computer actually cannot replicate that, right? So what is a color space? A color space is a subset of the entire visual spectrum of color that is being displayed, right? So computers display something in the sRGB color space. And this is a subset of all the colors that you can see with your naked eye. And it's really important when you're working across different softwares, when you're working with images and with color, to make sure you're in the right color space. Otherwise, you're going to be editing something that is not being represented truly as where it was, like originally came from. So here is a diagram, essentially. This like ovally shape right here, this is the entire human color gamut, where this is every single color that you can see with your naked eye, right? The sRGB color space is defined like this. It is a subset of all the colors, right? So you can't actually represent all of the colors that you see in your real life in a digital world, right? It's not possible because the color space itself just isn't encompassing all of these colors, right? So what ends up happening is that these colors and everything else gets mapped over or like squished into this tiny triangle, and that's what gets displayed. So you lose out on a lot of color information, and it tries to approximate all of this color gamut into this tiny triangle of the sRGB color space. Does that make sense? Yeah. Unfortunately, the sRGB color space kind of sucks. Obviously, it doesn't represent a lot of colors, right? So what we use instead is the ACES CG color space, which is my default color space. It is also the color space that is defined by the Academy for working in CG. And essentially, the ACES CG color space is this blue triangle over here. And you can see how it captures more colors. There are physically more colors that it can represent compared to the sRGB color space, right? So you're able to get more color accuracy because you're capturing more colors. But then you're like, wait, if computers only display colors in sRGB, then even if I'm capturing colors in the ACES CG color space, then like, does it matter? Because my computer could only display this tiny sRGB color space, right? If you remember what we're talking about with like the mapping, you're essentially doing all your calculations, you're doing your render in this larger color space, or I'm getting the correct color data information, like as numbers, in a more accurate color space. And then when I transpose that, or like when I compress that and like squish that into the sRGB color space, because I did my calculations in a more accurate color space, I'm able to display the color space a lot more accurately, or map it a lot more accurately when I finally display that on my scene. Where if I were to just do my calculations in the sRGB color space, then it's not going to even consider any of those like other colors out there, because it's not like doing the calculations in an accurate color space. Does that make sense? Yeah. So as a bit of like a visual, if I were to do something in sRGB color space, this is what it looks like. Well, if I were to do something in ACCG, this is what it would look like, right? So this projector, I'm assuming here, projectors might use a different color space than sRGB, but here, like, let's say this image that you're seeing on this projector screen is in sRGB, right? But the calculations that were done when producing this image is either in sRGB or in ACES, right? And if you look at the difference between it, in sRGB, like colors tend to be a lot more like washed because it's not able to calculate enough colors. It's not able to represent all these colors so that when it does the calculation and you're displaying this out into its final image, the colors tend to be really similar, right? You're not able to have a lot of dynamic depth or like high dynamic range, right? Like the colors are just not enough colors to be able to represent the scene accurately. Well, if I were to do this using ACCG, the colors are a lot more accurate because when I'm calculating it, I'm able to see like, okay, the shadows are a lot darker because in the true scene, in like the correct scene, the shadows are this dark. And it's able to represent and capture those colors, right? It's able to capture like this like brown like lighting and this like really bright glow that is not able to be captured over here, where it's like this is very clearly artificial. Well, maybe like this would represent real life or this specific scene a lot better because the shadows are supposed to be this dark, right? Now, this is very different than like artistic interpretation. You're like, okay, well, this looks better, right? The question here isn't what looks better or not, but what looks more accurate, right? Because if I wanted to look more like this, then yes, as an artist, I could just be like, okay, let me line up the scene, right? Let me change the colors, you can do that. But that's not the issue here. The issue is like, okay, I want to be able to capture what the scene actually looks like a lot better. So that's why we use ACCG and not sRGB. Make sense? Any questions? Okay, so yeah, this is really important when you're working with colors and you're working across softwares because you need to make sure that these color spaces are correct. Because let's say I did all my calculations in ACES, but then I'm reading it in sRGB, then things are just gonna look wrong, right? For example, let's say I like write out instructions in English for like how to do something, like step 1, do something, and using English, right? And I give it to someone, and they don't know how to read English, right? So they're like, okay, well, I don't know what language this is, but let me tell my translator it's Chinese. They're gonna have a really difficult time because you just told them it's the wrong language, right? You need to tell them it is English so that they can begin translating. So that's essentially an analogy for like why we need to set the color space properly. Let's talk about EXR files and AOVs. So when we're rendering our images, we will not be rendering them out in PNGs or JPEGs or those like really common file types. The reason for that is because those file types don't store that much information about color. Like PNGs and JPEGs, they just don't have enough information in that file type to be able to convey the amount of colors that we want it to be able to capture. So we're going to be using EXR instead. So EXRs, essentially, they're like the industry standard file format for like literally anything film related. And it basically allows you to store 32 bits of color, which is like a lot. I believe like JPEG plus or like PNG plus only stores like 16 bits or maybe 8 bits, I think is the default. Yeah, so it allows you to like store more colors, but it also allows you to store things called AOVs, which we'll get into in a bit. And also a bunch of metadata. So you can basically store your entire scene, your entire render into this one nicely packaged file format called an EXR. Unfortunately, EXR files are really, really big. They're massive files. So if you're storing this on Google Drive, I'm sorry, your Google Drive will probably explode. Additionally, EXR files, since they're very specialized, you can't actually view them in a lot of softwares. Like a lot of softwares don't support viewing EXR files, right? Like Maya does, After Effects does, Photoshop kinda does. You need to install like a separate plugin to be able to look at an EXR file properly, which is kind of crazy, like Photoshop really, right? So it's really important as well when you're doing EXR files to set the right color space. So your EXR file will store the color space that is in, but it'll also it won't store the color space that you were originally viewing in as well, right? So you need to know the color space that you're working with. You need to know the color space of the EXR file to be able to actually view this properly. So if you go online and be like, oh, EXR file viewer, and it will like kind of work, but it'll just look wrong, right? And the reason is a lot of these online EXR viewers do not get the right color space data, they're not doing the transformations properly, and it just isn't correct, right? So make sure you're using specialized software for it, using Maya, using After Effects, things like that. And make sure your color spaces are correct. So AOVs, what are AOVs, right? It's like you can store these in EXR files, like what are they? AOVs, or stand for arbitrary output variables. They basically allow you to render specific data into its own AOV or render layer, essentially. And it's really useful for compositing. For example, here's some common AOVs. I think a visual example is a lot better. So over here, this is your beauty AOV. This is the default AOV that is rendered with every single render, right? It is your final image. It is your beauty shot. It is the image of your render. However, if I wanted to isolate very specific data out, I could also do that. Or I can define an albedo AOV, which is only the diffuse, right? I can turn the diffuse into its own image. I can turn the emission into its own image. So in this area, like robot, like its eyes are glowing, right? So it only has this emissive property in the AOV. I can render out the specular independently, right? Or this is only the color that is being contributed by the specular is being rendered into its own AOV. This is the Z depth, which is like the AOV that corresponds to the depth and the distance, right? So closer objects to the camera are black, while farther objects are white. So I can basically get the depth of the scene as data that I can work with. Additionally, you have the motion vector, which is you're representing how fast something is moving in the scene as an AOV. So you can kind of see how this would be useful in post-processing, where I'm like, okay, I like how this looks, but he's just a bit too shiny. Like, I think I messed up the specular, he looks a bit too shiny, I don't like that, right? What you could do is that if you had an AOV that only had the specular, you can just lower the specular in post, because the specular AOV that only captures the specular property of this shader, of this material, is rendered out on its own layer, right? So you can like reduce this, and you can basically add up everything else, and now you'll get a less shiny version of this person, or this beauty shot with less of the specular attribute applied to it, right? These other types of AOVs are useful for other things besides like the final image, right? So let's say I want to do like depth of field, where I want far objects to be blurry and closer objects to be focused, right? It's not possible to do that unless you know something about the depth of the scene. You need to know how far these objects are, right? So in a lot of these post-processing software, these compositing softwares, you need access to the Z-depth buffer or the Z-depth AOV to be able to see how far an object is, right? And you can say, okay, all pixels related or past this distance in the Z-depth will be blurred, right? And that's how you're able to do depth of field in post. Same with motion blur. Like if I want to be able to blur really fast objects, well, in post, it needs to know how fast an object is going, right? Then using the motion vector AOV, since you're able to get that information, get that data out, then you're able to like, okay, this is the fast object right here, I can blur that, right? While everything else, I can not blur, right? So that's how you're able to like motion blur in post as well. Questions? Yeah, realistically, you probably won't be looking at these AOVs, but they are really nice to know if you want to get into more compositing workflows. Cool. Here's a note on real-time rendering. So you're kind of like, okay, well, I just spent this entire like part of the lecture talking about like how rendering takes forever and it's so long and there's so many computational resources. But when you play a video game, you're like, well, I play like Cyberpunk and it looks really, really good. And you're like, what the hell? How do they do that, right? Like, it looks really good. They render things out, but it's like real time, like instant as well. Like, why can't they just do that in film? Like, what? You're saying that like the interstellar black hole took 3 months to render? What? That's crazy, right? True story, by the way. Yes, the interstellar black hole did take like 3 months to render. I think like a single second took like a month, which is kind of crazy. But yeah, so yeah, like how do these do it in video games? And the answer is like they cut a lot of the corners, right? Video games do not look like Pixar films for good reason, right? And the reason is because video games cut a lot of corners. And one such way that they do this is remove something called global illumination. which is essentially, you know how we were talking about like light hits an object and it bounces and it bounces again and it bounces, right? That is global illumination. When light bounces, that's called global illumination, and a vast majority of video games just do not do that because that is the primary thing that adds to render times. And by not doing global illumination, you don't get indirect lighting. However, you can render a lot faster. Additionally, you can also bake your lighting. So a lot of video games are static, like the objects and the floor and the materials, they don't move, right? So you can light a scene, and then you could turn that lighting into a texture, and then you could just apply it to the texture, right? And then that way you don't have to do any lighting at all because it's just the texture color that is like pre-drawn in, like you draw the lighting in, right? And that's called baked lighting. So you can just take that lighting information and bake it in, and that's how a lot of video games do it, where you just store the lighting information. And even if the character moves, even if the object moves a bit, it's like good enough, right? And they don't have to calculate lighting at all, which is drastically reducing render times. Additionally, there's like various sampling optimizations, baking detail, where like maybe something is just a cardboard cutout instead of an actual mesh, right? Or they also use GPU rendering, right? They render on the GPU instead of the CPU. Maybe they don't have access to enough features that a CPU renderer has, but they don't need those features because it's a video game, right? So that's how video games do real-time rendering, essentially. It's just a nice, fun to know. Okay, let's talk about our render farm. So we do have this render farm set up here in this computer lab. Every single one of the computers that you see here is a render farm, like node essentially. It's really funny, like when you run the render, all these computers turn on at once. The room gets a bit hot. It gets a bit toasty, you know, it gets a bit toasty, a bit warm. It's not like unbearably hot, it's just like warm, you know. Like slightly uncomfortable, like yeah, a bit stuffy, a bit uncomfortably warm, but not enough for you to complain, essentially. Yeah, so this is render tracker. We'll be posting instructions on how to use these computers once render week starts. But it's nice. Using these computers is also, we do have a process for if you want to render remotely through your like computer at home. So you can be at home, you can send a render over to this farm, and then it'll like run the render and don't even need to be here. Downside of that is that it does require you to put commands into a terminal, and it is kind of technical, and things might go wrong. So there'll be instructions if you're interested. It's there, but things might go wrong. So yeah, this like render farm isn't perfect. I set it up, like I worked with the EECS department, IT department, to set this up last semester. It should hopefully work, fingers crossed. But if it's buggy, I'm sorry. But yeah. Alternatively, you could local render. So instead of using it as a farm, every single one of you has access to creating an account on these computers. You could boot up these computers, Maya's installed, Arnold's installed. You could just download your project onto here and just run it on the computer and then run it overnight, right? So this is actually what we used to do before we actually had farms, where we literally like, when I was a student, I took 5 or 6 computers, I started all of them out into a bunch of different renders. I'll put a piece of paper that said "do not touch," and then I just like left it on overnight, and then I came back the next day. I was like, oh, the render's done, right? You totally could do that. You can leave these computers on overnight. They're on 24/7. They don't turn off. Yeah. Downside is that if someone comes in here and then they like click the escape button, then your render stops, and it's kind of sad. So just like put a piece of paper on there. It says like "do not touch" in the process of rendering. It's also really slow because then you're using sequence rendering instead of distributing all of these frames. But it does work. It just might be frustrating. Or you can render on your own computer. You can also do that. Yes.
Compared to like rendering on a single computer versus the farm, like how much quicker would you say the farm is?
Oh, I think we had some statistics, but I don't really remember. I think we were able to render out 4 days of sequence rendering in like 20 minutes. So yeah, it's really, really fast. Really, really fast. Yeah, you're essentially dividing your entire render time by 30, essentially, because there's 33 computers in here. Yeah. Any other questions? Cool. Word of advice, a lot of things can go wrong during rendering. Like, a lot, unfathomably a lot of things can go wrong. Here are some examples of things that have gone wrong in the past. Textures don't appear; they're gone. All your textures are gone. You're like, what the hell, right? Your color spaces are wrong, so your colors just look wrong. Your meshes suddenly disappeared, right? This usually happens if someone doesn't set their project, right? And the mesh and the reference is in their downloads folder, and then now no one else has access to that folder, right? Especially when you're using these computers, where it's like these computers don't have access to your file system, like 100% no way, right? So yeah, make sure you set your project, make sure everything is in your project. Otherwise, you'll have disappearing meshes, or they might just disappear anyways because rendering is really finicky. Unable to render in time. You should not be rendering on the day of showcase. We've had people render during showcase, which, as you can imagine, is really, really, really stressful. And a lot of times they're not able to render in time. We've had people submit play blasts to showcase, right? So please, I really hope that doesn't happen to any of you. But please render ahead of time. Rendering takes a really, really, really long time. A lot of things can go wrong. It's really stressful. So please render early. Also, someone used Maya 2023 while everyone else is using Maya 2022. Has happened before, right? Where someone is using another version of Maya and you're like, hey, I'm using this feature that is only available in this one version of Maya, and then everyone else is using a different version, and then everything breaks, right? So that's why we super stress, make sure you're using 2024, make sure you're installing that one specific version of Arnold that everyone should have installed, right? So just things that have gone wrong. So what do you do, right? Things have gone wrong, everything on fire, what do you do? Yeah, you start panicking, because panic is definitely the right thing to do, right? Just kidding. Instead, you should just accept your defeat. Good luck, bye. Just kidding. So if and when stuff does go wrong during rendering, contact a facilitator. We're here to help you. You're probably experienced. You probably have encountered your problem before in the past. Send a message in Discord, right? If you're not able to physically contact us, send a message in Discord. Discord is a great way to contact us. Just don't DM us, right? But send out a message in Discord. Keep calm. You got this. Panic doesn't help. You'll be fine. Just breathe. Also communicate, right? Don't wait until the last minute to let us know that there is an issue, right? So if there's an issue, be proactive about it, really communicate. Also, we'll be having really massively extended office hours during the entirety of RRR week, which we call RRR week, which is reading, review, rehabilitation, and rendering. And so by massively extended office hours, I mean every single day from 12 p.m. to 9 p.m. So in this room, in person and online. So yeah, please give a thank you to our facilitators over here. Woo! Yeah, that's 9 hours every single day, except Friday, because Friday is showcase. So we'll have office hours until 3 p.m. instead. But yeah, please utilize this resource that we have for you. We're here to help you. And yeah, let's move on to the compositing section of this lecture. Before we move on, does anyone have any questions? Yes.
So showcase is during RRR?
Yes, it is the Friday of that week at 4 p.m. 4 p.m. Okay.
All right, now it's time to get into compositing, not to be confused with composting, although that's something you should probably be doing. This is where all the I'll fix it in post comes back to bite you. So. We have another video about compositing as well.
In today's films, it is possible to create almost anything. But the work is definitely not that easy. It includes many hours of attention to small detail, lots of creativity, and a high level of skill. This world is called VFX and is built from many parts in a long pipeline that creates something amazing. And that's what you see on the big screen. The last role in this long pipeline of visual effects is called digital compositing, which is a creative process of assembling filmed and rendered elements from multiple sources to create a final lifelike illusion. What is that, you ask? Let me show you. It's a profession that includes many skills such as rotoscoping, which separates the foreground from the background, and there are all kinds of techniques to accomplish it. In films, it is common to use a blue or green screen to easily remove the background from behind the actors, and that is called keying. And by doing that, we can create a more realistic background behind the actor. Tracking is another side of the story, and it is very important to know how to do well. There's 2D tracking, and there's 3D tracking, which recreates the exact movement of the camera. Another big part of this job is to remove objects, cables, and trackers, and paint them out and insert something else instead. And, of course, there's computer-generated elements, or, in short, CG compositing. But my friends always say VFX looks fake.
Now that we know the general gist of compositing, let's put it all together. This is going to be an example from your guys' compositing lab that you must be doing for this week. Here we have a background set that we'll be using. We can see that there's going to be some transparent areas that we'll be applying this sky background to. And then we'll also be using some effects right here, along with some shadows that we'll be having over the background set. Some water that we'll be having within the specific scene as well. Some foam effects that will be overlaying onto the water. And then once we put it all together, we get to something like this. Yeah, and that's the power of compositing. So for this week, individually, you guys will be completing the compositing layer management lab, which has optional components of motion tracking or particles, which you can do for, you can do either of those for some extra credit. Additionally, okay, I'm pretty sure some of you guys have completed the animation animatic feedback on Discord. If you haven't already, make sure you do so. This is a grade. For your groups, you guys will be hopefully finishing up animation and lighting. We would recommend at least rendering one image from each set and also rendering out one scene entirely for your short. The rendering lab will walk you through this entire process and make sure you reach out if you guys do need help with this specific task. For the remaining weeks, next week we have Michael McCurwitz coming in on Thursday from 7 to 9 p.m. for a talk. He's going to be talking about his experience as a Pixar animator.
Ex-Pixar animator.
Yeah.
He worked on The Incredibles and Cars and
Ratatouille.
Ratatouille.
So yeah, an extensive background. And additionally, after that, we're gonna have our week, reading, review, recitation, and rendering. Starting May 4th, we'll be having office hours from 12 p.m. to 9 p.m., like we said earlier. As a reminder, rendering does take a long time and could go very wrong when there's errors, so make sure you guys start early. If you guys need help at any point, make sure you reach out to us during office hours. We are here to help you. I cannot restate this enough. When preparing for Showcase, make sure that you submit a fully rendered and compositive short to us before Showcase, which is going to be on Friday, May 8th at 4 p.m. Preferably, you should submit it in earlier than that. There's going to be a Spring 2026 Google Drive that you'll be submitting your animation to. Please remember that compositing a short still takes time as well, just kind of like rendering. So make sure you export a compositive video and plan ahead for that. We don't want to see you guys playing your short straight out of After Effects, please. So make sure you have it all composited and submit it. Additionally, facilitator applications are open for fall 2026. If you're interested in becoming UC Bug staff and want to apply, our only requirement is taking at least UC Bug Basic, which you all already have. You don't really need to have extensive animation background as long as you're willing to learn. We'll be willing to accept you into the team. UC Bug is completely run by students, so we're completely reliant on you guys to help keep this like decal alive. If you want to help and support more of what we do, please consider becoming a facilitator. I believe you can get credits for being, you can get units for being a facilitator as well if you have facilitator training. I don't think there's any more facilitator training this
I think there's one next Tuesday, maybe.
So, yeah.
But there's high demand.
Yeah, there's high demand. So it's going to be pretty competitive if you want to be able to get units for next semester. Sign up for that facilitator training and then fill out this facilitator application form, and you'll be a part of the team if you get accepted.
Alternatively, there are some underhanded methods we use to get units. Enrolling into the course that you get for units. Yeah. You do get units as a facilitator. So.
And thank you. This was technically the last lecture of the course. I think next week will just be like work time, right?
Wrapping up, like final notes, and then work time.
Yeah. So, thank you.
That's Dan Garcia, our faculty advisor.
Yeah. So, good luck, and go finish your shorts.
And have fun.
And have fun.
Attendance code.